Hey guys, so SideFX asked Syntagma to have a look at some new tech that was coming down the pipe, and these are kind of the first results. What I want to mention here is that PDG and TOPS clearly wasn't intended for design work first. It's first and foremost still a pipeline tool, which allows you to build huge intricate pipelines easier than ever before. However, what I was interested in was kind of using and abusing it to figure out if and how it would fit into a small studio or freelancer workflow that is mainly focused on procedural design. And while the first steps were kind of alien a bit and somewhat frustrating at times, I must admit, in the end I think the tool is quite useful, even for a single artist or a small studio, as it can accelerate certain workflows and certain steps in your processes. So let's get started and have a look at how you can use PDG and TOPS for procedural design. To talk about the very essential idea behind PDG and TOPS, let's have a look at a typical setup that you might encounter when doing design work in Houdini. So what we usually do is we set up some initial values, tweak them, and then, for example, in this case, let's run a smoke simulation, just some nice and quick pyrosim. And then let's drive an instancer by the smoke simulation's values, for example, using the smoke sim's velocity attribute. And finally, render this out. And usually we would go through these steps sequentially. We would first dial in some values, then run a smoke simulation, then have the instancer influenced by those smoke sim's values, and render out a sequence. And what we usually do when trying to dial in values is we set up different initial values, in our example 3 different initial values, and then again step through this whole scene sequentially. We run the smoke simulation with those new values, drive the instancer with the smoke simulation, and again render out a sequence. And in our case, let's just assume that one single smoke simulation, for example this one here, runs for just 5 frames. So before we could render out a single image, we would have to wait for the smoke sim to finish, and then the instancer to do his work, and then the render engine can kick in. But what if we now had some mechanism that determines which part of your scene is dependent on which part? Well, this could come in handy, especially if you have parts of our scene that are easily parallelizable. So for example, the instancer, as soon as it's got its values from the smoke sim, it can be run in parallel, and the render engine can kick in parallel if we have multiple instances of the render engine running. So what, for example, could happen in this case is, instead of Houdini waiting for the whole smoke sim to finish, and then running the instancer and then the render engine, Houdini would realize that after running the first frame of a smoke simulation, we can already run the first variant of our instancer, and as soon as that's finished, we can already render it out. So in theory, if you've got a lengthy smoke simulation here, this should give you a quicker time for the first frame to appear. And of course, this will make a bigger difference if your scene is especially heavy. Also, of course, what could come to mind is distributing those render jobs onto a farm, for example, or even distributing those geometry creation jobs onto a farm and have multiple machines working on them simultaneously, making the overall setup quicker. And the really crucial part of this whole thing is that you need some automatic mechanism in the background which detects which part of your scene depend from which other parts of your scene, how do they branch out, how do they influence each other, and determines when Houdini can start working on a given part of your setup. And that is exactly what PDG is, a procedural dependency graph, a method of determining which parts of your setup depend on which other parts of your setup. Admittedly, this is most relevant to big pipelines and big scenes. However, here and there are some neat techniques which we can adapt into also small-scale workflows, especially when looking at some tools that ship with PDG. Okay, so before we dive into Houdini, just a little disclaimer. I'm recording this while still in beta, so there might be changes to the final release version. But, I mean, you have to start recording at some point. So, here we go. For our very first TOPS and PDG setup, I want to start simple and build a setup that is heavily relying on wedging. So right after graduation, a few friends of mine had a client who requested a run of posters. And as far as I can remember, he requested 5,000 or 10,000 posters, with the twist that each poster be an individual frame, an individual rendering. Back then, I think they resorted to doing this in code and using some processing. But now let's build something similar in Houdini. I want to create some abstract shapes that I can drive by a few parameters. Let's start by building our geometry using a geonode. Call this sails because they resembled somewhat abstract sails or just cloth floating. And the very first thing I want to do is drop down a circle, set its type to be a polygon, have 24 divisions, and set this to be an open arc ranging from 0 to 180 degrees, so a half circle. Next, I'll attach a copy and transform to this, set the total number of copies to 40, and then dial in some rotational values along all axes, something like this, so that I get these lines oriented in 3D space, just forming this shape. To turn this into a polymesh, I'll attach a skin And the default settings just work fine for now. I mean, I've got some intersections here, which I, for now, can resolve by dialing in some different values in here, but in the end, they won't matter that much. Also, what I could do is slightly increasing the scale in here is just really, really sensitive. So something like this. So we get these organic shapes that are driven basically by these transform parameters here. Let's disable the grid and attach a subdivide here, just so that I can increase my mesh resolution. Set its depth to 2, so I get a high resolution mesh like this. Then normals on this mesh would be fine just for rendering later. So here we go. And finally a transform. So we can move this around or rotate it as we like before piping this into a copy to points. So I want to build a standard instancer, one of the very fundamental setups of motion graphics. And in order for the copy to points to work, I need template points, which I'll generate using a circle, which I set to polygon 2 along the ZX plane. Have this thing have only 3 divisions for now. So I'm only creating 3 copies in the end, and wire this in here directly. And now, I mean, this already looks somewhat promising, but I'd like to have those copies oriented onto those points. So that means I want to rotate them individually. And in order to be able to dial in those rotations, I just want to drop down a resample first, which I'll simply use to generate a curve U attribute. That means we are writing a, whoops, let's uncheck that. So I'm using this to generate a curve U attribute here, which ranges from 0 on the first point of my circle to 1 on the last point of my circle. Next, I'd like to get each point's normal by dropping down a point triangle. And as long as my circle sits on the center, being centered at 0, 0, 0, I can generate an outward pointing normal, call it n, by just normalizing each point's position. Like this. And now my copies point outwards. Let's just highlight this here and show the normals so they point outward here. Also at this stage I could delete everything but the points using an add, which I'll wire in here, and then check delete geometry but keep the points. So we end up with this. So now comes the funny part. I'll just write a few lines of vex in order to be able to drive the orientation. That means the rotation of those objects that I'll instance on those points. So what I want to do is drop another point triangle, and in here we're going to create a quaternion. That means a vector with 4 components telling the copy to point stop here how those copies will be oriented. So let's create that vector 4, call it O for orientation. And by default, I would like to orient my copies so that their x-axis points into the direction of the normal that I created. I'm going to use the dihedral function to calculate this, and I want a vector pointing from x so that it points to our points normal like this. So far so good. Next I'll create 3 float sliders for our 3 angles along the x, y, and z axis. Rotation x equals to float slider. Rotate x. Let's create that. Let's see, just created a float slider here. Let's copy this and paste it 2 more times. This time calling it y and z and renaming the variables respectively and creating those sliders. Also, I want to head in here and go to edit parameter interface, highlight these 3 interfaces and set their range from -360 to 360. Also, most of my calculations will use radians instead of degrees, so let's directly convert those using the radians function, which again, I'll just paste to the other lines here too. Now that I've got those 3 angles, I'll just build a vector out of it. And yes, I could have used a CHV expression here to have a vector interface directly, but I like those slider interfaces here better, so that's why I went with those. Now I'll convert those to a quaternion. Call this one rot for rotation. And use the Euler to quaternion function to convert those. Finally, let's take our original orientation vector, which we calculated up here using the points normal, and multiply it with our new rotation vector, which takes into account those manually dialed in values. And we use the Q multiply function because we're dealing with quaternions here. So we multiply rot and O. And finally, I'm going to write out our O value to a vector 4 called orient. Like this. Let's keep our fingers crossed. Highlight this before and after so we can see there's something happening, and let's try rotating this. So yeah, that's working too. And there are easier methods or other methods of doing this, but using a quaternion is not the easiest, but a rather safe way of orienting copies and instances in Houdini using the copy to points. Also, what I want to do up here is I'd like to be able to remap those rotational values depending on where we are, on which point we are. If you remember, that's why I created those curve view attributes before. So let's check if we have an integer called remap over points. Let's create that slider and again head into our parameter interface here and switch this out to be a toggle. So I can just toggle remap over points on and off. So if that integer is true, we multiply our angles by a value, and let's use a ramp to remap our curve view. Call this one ramp angle, like this. So if I check remap over points and dial in some value, you can see, depending on which point the instance is sitting on, it gets rotated increasingly, and I can dial in this a bit more precise using that curve down here, that ramp. So that's our basic setup, everything normal, everything standard, nothing special so far. Keep in mind, however, that one of the main driving forces behind the appearance of this abstract thingy here are the transformation values, which we input here into the copy and transform. So when we dial in different values, this thing changes shape, sometimes pretty drastically. So assume we have a client who seriously wants 4,000, 5,000, 10,000, 20,000, 100,000 variations of this, and finds a printer who is willing to print those. What we definitely could do is just animate those values. However, finding out every combination of those values would be a bit tedious, because you'd have to go back again, resetting those values, then increasing those values, etc., etc. So what we're trying to do here is finding permutations. That means every possible variation there is of this sculpture, when changing those three, and maybe let's take into account the shear too, because that drives the appearance too. So maybe let's take those three and this fourth parameter here and try to find all possible permutations within a given range. And for that, I'll finally use tops. So up we go, and we drop down our top net here. Dive in there. And the first thing we need to talk about is the local scheduler. So your newly created top net is not empty. And the local scheduler is a node which drives how PDG and TOPS distributes the workload on your computer locally or on a farm, with the local scheduler meaning that the workload will be distributed locally. You can set up a few parameters in this node here. For example, the working directory, set to our current HIP file location, and the maximum number of CPUs to use. And by default, it is currently set to -1. Again, this might change until release, but -1 meaning that PDG can use all processing power of your computer to work on your setup. Now, in order to output variations on my setup, what I need to do is called wedging, and it's not a new concept. It's been there in Houdini before, but with TOPS, the whole workflow changed a bit. So what we're going to use here is a so-called wedge node, which will generate variations in an attribute or multiple attributes. So let's add one wedge attribute here, call it Rx wedge, for rotation X wedge, and now we have several settings of how we want to drive and influence this parameter here. In my case, I want to have it in a range from, say, -15 to 15 degrees, and just for now, for the beginning, let's just enter a wedge count of 2, so this will only be subdivided in 2 steps. There are other options of how the wedge node could generate these values. For example, we could directly input a single value, maybe drive that with an expression, or we could input a value list, so we could dial in multiple values here through which the wedge node would then iterate. However, let's just stick to the range, so we will subdivide this range here evenly, for now just into 2 values, which we will then pass on to our setup. Speaking of passing on those values to our setup, let's just copy this attribute's name here, head up and go back into our sales setup here, and into our copy node here. And what we want to do is we want to drive this rotation value by this parameter, so let's just paste its name and add an @ in front of it, like this. And for now this evaluates to 0, which shouldn't trouble us now, and we're not going to worry about this now. Instead, what we're going to do is go back into our top net, just duplicate this wedge here, attach it to that one, change the value name to our Y wedge, and again, copy this one more time, attach it here, call this one our Z wedge. And let's just copy this name again, head back into our sales setup, and in here, let's paste our RZ wedge, and here, let's change this one to our Y wedge. So now I've got these 3 parameters. Let's just check. Yeah, of course, this is a typo here. Yeah, so now I've got these 3 parameters. They currently evaluate to 0. Again, I'm not going to worry too much about this now, which will result in this not very intricate sculpture here. Another thing I'd like to wedge is this shear component here, the shear X. So again, back into our top net, let's just copy the first wedge and append this before. Call this one shear X wedge. And this one is really sensitive, so let's have it range from minus 0.05 to 0.05, like this. Again, copy this name here, back into our sales setup, and into the copy sub. Let's paste it here in the shear X, like this. Let's save this and head back to our tops. Now that I set up my wedge chain so far, let's generate those work items that the wedge generates here. And we can do that by either right-clicking on the node here and heading to Dirty and Cook selected node. Dirty meaning clean the node or reset the node, and then cook it, so evaluate it basically. Also, I could just press Shift and V. Let's do that, and we can see we generated those two tasks here. And when I middle mouse on one of them, we can see the first one here has a wedge index of 0, wedge num of 0. The second one here has a wedge index of 1 and a wedge num of 1. And this is the parameter value for the wedged parameter that it outputs. Let's do the same thing for the next wedge. And we can see we have now 4 tasks here, with the first 2 spawning to those, and the second 2 spawning to those. So we are slowly generating increasing numbers of permutations here. Again, let's middle mouse click on them, and I can see now my wedge index again is 0, with this one 1, and this one 2. And you can see something weird happening here, because the wedge num is now being reset to 0. So later, when we want to access those individual permutations here, we should stick to using the wedge index, and not falling for the wedge number here. Again, let's just highlight this one downstream here, hit Shift V, and we can see we are ending up with 16 permutations. So when we start here, we can see the whole tree that spawned from these individual permutations here. And also, when highlighting those individual tasks here, we can see our whole setup automatically evaluates with those wedged values that we output for each individual task in here, and builds our geometry using those wedged values. Now, what I'd like to do is cache out this geometry. I could feel tempted to render this immediately. However, especially if we're dealing with heavier geometry later, it makes sense to cache out those results. And for that, we're going to use the ROP geometry top, which wires down in here. Let's just flag it for output. And this one needs to be pointed to a SOP, which it should evaluate. So let's just quickly head back to our sales. And I've already attached a null in here, called it out. So let's point it to that in the ROP geo. Let's just point it to sales out like this. And for the output file name, we don't want to use the current frame number in our file name, but we want to use this wedge index here instead. So let's delete the $F and do a backtick and another one, and then let's just write add wedge index in here. Let's just middle mouse on this and highlight one of our tasks back in here, and let's save this and cook this one. Shift V. So we can see this cooked now, and if we middle mouse on one of those tasks here, we can see there are no errors here, and when right clicking on it, we can view the task output. And if we click on one of those tasks here, we can see we generated those geometric variations. So let's load those files back into our setup for rendering. I mean, we just cached it out, so let's just read back those files. And to do that, I just want to copy this parameter here with the output file path in my ROP geometry, head up to my sales here, and drop down a file SOP. And in here, I will just pass the relative reference to my ROP geo file path here. And I can now see with this one, when I middle mouse click on it, it evaluates perfectly. And in my topnet, I can still switch my different variations, and they will be loaded into my file SOP here. Let's head back to our topnet. So now that we cached out our files, let's set up rendering by heading up one level, dropping in a camera, control clicking there, just maybe adjusting the camera so that we have some nice framing like this. And then let's head back into our topnet, and just for a quick preview render, let's drop down a mantra ROP, wire this in here, set its rendering to a really low quality so it renders fast like this. And then in the images tab, let's for the output picture not use the frame number, but again our wedge index to drive the file names for those. Let's save this, select our ROP mantra and hit Shift V to cook this. And you can see while mantra is chugging away here, we've got 11 tasks being worked on currently, 5 to go, and as soon as tasks are finished, we can see them up here. So now that they are cooked, let's head to our working directory, and we can see we have some render results here. Let's just check on them, and yeah, that looks like a really coarse preview rendering of our geometry. And while this use case with its current setting is not as impressive, let's maybe increase those wedge settings to something more realistic, and instead of always outputting only 2 wedge values, let's output 10 for each wedge. And let's just recook the last wedge here. And let's fix the layout. So you can see with 10 wedge values, we are escalating really quickly, starting from 10 values, going to 100, 1000, and then 10,000 different variations here, which would make for a nice series for our whole poster run. They would take a few hours to cook in here, so we can let this run overnight or even let this run distributed. But that's a topic for another tutorial. So that is the very first and very basic TOPS and PDG setup. The main things to keep in mind here are, on the one hand, in our file paths, if we use the wedge index, let's stick to this syntax using the backticks and at syntax, and also using that very same file path in our SOP level when we load back in those file caches here, just using a relative reference. Apart from that, I really like how you can see the complexity that arises from those few wedges and few variations that we're doing here, and I think this really drives home the explosion of permutations and variations that you can get out of such a simple setup. So let's build on this in the next tutorial.